Welcome to the lectures for Class 7 of Artificial Intelligence. And in today's lecture, we're going to work together on more working with lists in Prolog and also looking at control in Prolog. And this is based on the material in our Prolog book, chapters 6 and 10. So let's start by remembering append. We'll have a little bit of fun with it, but we'll start out by recalling how it works. So the basic idea is that if we're going to append an empty list to any list, that the resulting appended list together would simply be the second list. That's our base case. The recursive case is that the first argument is not empty, in which case it has a head and a tail, and we're going to want to have a list that where it's going to result from the head and the tail being appended to L2, and the third argument should be all of that. Now, the head of the resulting list, the one that appends the first two arguments, clearly has to be H. And the rest of that list, so here's H, and the rest of that list here we'll call L3. What is L3 going to look like? Well, it's going to be all the elements in T here, followed by all the elements in L2. And so we call append recursively to do that. All the elements in T, followed by the elements in L2. And basically, we keep stripping off elements from T until it's the empty list and the base case is found. All right, now we can use append for other purposes. So and define new predicates with that. So, for instance, if I want to find out if a list is a prefix of another list. So, for instance, maybe the list AB is a prefix of the list A, B, C, D, E, and so forth. I can define that with append. Basically, what we need to do is say that this list P is a prefix if P appended to anything results in L, right? Because P will be the first part of L, therefore it's a prefix, regardless of what's here. And what's more, because we can backtrack, we can find out all the possible prefixes of L. Same thing works for suffix. So, so if I have some list S, and I want to find out if all the elements in S are the final elements in L, well, I can do something similar, the opposite of prefix. Basically, I don't care what the beginning of the list is, but if S is the list that would be used to create the appended list L, then I know it's true. In other words, S is going to be the same as the last set of elements in L. And finally, we can define last this way, and I'm calling this my last again because there's already a last built in, but here's the idea. I want to find out if X is the last element in L. So again, I don't care what the initial elements are, but if anything appended to an element of one list results in L, okay, then this one element is going to be the last element of the appended list. In other words, L here is going to consist of all of these elements followed by X as the last element. Well, that means X is the last element, so I can unify this X and this argument, and I get last. Let's try these out using the SWI Prolog interpreter. So I've consulted that file that I have my examples from, and we'll give it a shot. So First, let's try prefix. So if I say prefix 1, 2, 1, 2, 3, 4, we think this should return true. Oh, by golly, it does. All right, what about this one? And sure enough, returns false. Now the cool part is I can find all the possible prefixes. Let's see how that works. So I'll just say prefix, and we'll call it P of my sum list 1, 2, 3, just to keep it manageable. So the empty list is a prefix, that's right. The list containing just one element 1 is a prefix, 1, 2, and 1, 2, 3, because we know that the tail of that list is, the whole list is going to be the empty list. And that's it. Okay? Let's try suffix with the same idea. Suffix of, we'll call it S, and we'll do 1, 2, 3. And let's see what the different suffixes are. Okay, so the whole list is a suffix, right? 2, 3 is a suffix, 3 is a suffix, and the empty list is a suffix as well. So that's exactly what we want. And finally, let's try my last. All right, so we know, for instance, that using the built-in predicate last, if I say last 1, 2, 3, 4, x, let's call it, I should get out x equals 4. Terrific. Now we'll try my last. And we'll just copy this. And sure enough, x equals 4. Should we trace that just to see how that works? Okay, so we call my last, that's our original call, and now it calls append. All right, so the deal is that we know that if we have this list 1, 2, 3 as the front of the list, and 4, that gives us the list 1, 2, 3, 4. And of course, Prolog unifies these two arguments, this argument and this argument, in a way that makes that true. So sure enough, my last is 4. Next, I'd like to move our attention to the idea of reversing the order of elements in a list. And the naive way to do it, which is logically correct, is that our base case is going to be the empty list. So if we reverse the empty list, we obtain the empty list. Then if it's not empty, there's a head and a tail. Okay? So what we do is we basically do a naive reverse of the tail. Okay? And we append this reverse tail, which will be the rest of this list backwards, to the list with head, and that'll create the entire reverse list. And as I say, that's logically correct, but it has some problems because we keep appending the same lists over and over again. In other words, we're going to be appending all but the last element or first element of the list the first time, all but the first 2 elements, all but the first 3 elements. So we keep appending again and again. So that's not very efficient. So the better way to do it is to use what's called an accumulator. So here's the idea. Let's say I have some list A, B, C, D. And I'll have another argument called the accumulator, which will be empty. And my plan is, now I have access to the head of the list, right? Because I've got the head here and the tail here. So I can take the head of the list and put it in the accumulator, leaving just the rest of the list. But now I have access to B, and I can make the B the new head of this list, leaving C and D, right? And now I can have access to C, so I can make it the head of this list in the accumulator, leaving D. And then finally, I've got access to D. It's the new head of the accumulator, leaving the empty list. And voila, I've pulled the elements off one by one from the head and pushed. So I've popped these off and pushed them into the accumulator, thereby creating a reversed list. Now, we don't really want to have to call every time we want to use reverse something with an accumulator. We really rather just call reverse than worry about extra arguments. So what we're going to do is define reverse of a list in its reverse as accumulator reverse with three arguments: the list, which we are going to reverse; the accumulator, which is initially empty in our algorithm; and finally the reverse list. And now our challenge, of course, is to write accumulator reverse. So let's do that. So here it is. So remember, I said the idea is to strip off the head and basically push it. So we've got H, which is the head of the unreversed list, and I will put it as the head of element of the accumulator. And initially, of course, it's empty, so that makes sense. And R we'll worry about at the end, because we won't worry about R until we've got our entire accumulator done. Then we call acc_rev again with the tail, since we don't have to worry about the head anymore. Our accumulator with the head in it, and R, which we'll worry about later. And we call acc_rev. Well, there's a new head. We'll put that as the new head in the accumulator and try to reverse T, and so forth, the new T, and so forth. Eventually, we'll strip off all the heads of the list, every element list, and we'll reach the base case, which is here, which says that, so when the original list is empty, what that means is we've popped the elements off of this list, pushed them onto this list, and thereby reversed it. So the accumulator has the reverse list. So if we unify the accumulator with R, then R will now be the reverse list. To conclude this part of this section of the lecture, let's try out these approaches to reverse. So let's start out with naive rev, and let's say we want to reverse the list 1, 2, 3, 4, 5. Sure enough, it reverses the list, but let's see how it did it. So copy this, and we'll take a look. All right. So far so good. And but then after we get to here, we're going to have to start appending back to do that. So we append the list with 5, then we append the list with 5, 4, then we append the list 5, 4, 3, 5, 4, 3, 2, and so forth. And so we end up with a lot more calls than we probably needed, and we're just doing a lot of extra work. Let's try doing it with our more sophisticated rev. 2, 3, 4, 5. And here again, we'll call trace, but you'll notice that what we're doing is we start out with accumulator empty. Now the accumulator has one element in it. Now it's got the first two elements of the list, the first three elements, and so forth until it has all 5 elements in. And now we can just exit back up without having to do any other work, and it's much, much easier. Having looked at together lists and manipulation of lists, we turn our attention to altering Prolog's behavior, how to control the way that backtracking works. And we'll start by discussing the cut? Well, it's represented by an exclamation point, and it's a kind of term. It's a kind of term with a single character, but it's a term nonetheless. Now, the thing to know about the cut is that as a term, when Prolog tries to interpret it, it always succeeds. But it has a special property. It commits Prolog to any choices that were made since the parent goal was unified with the left-hand side of the rule. So let's say that some parent goal, p of x, where x has some value, is now unified with this expression with p of x, and is trying to prove p of x, with x unified with that value. Well, if b of x fails, or c of x fails, it'll backtrack, and it might, earlier on in the program, come up with a new way of calling p of x with a different value. And that's fine. But let's say that b of x succeeds, c of x succeeds, the cut always succeeds, and now d of x fails. Well, what's going to happen is that it's going to try to backtrack. But but p of x, when it was called here with this cut, commits Prolog to the choices of the values for x we have. So it's just going to fail, and it won't get retried. That's the basic idea. Let's look at this in action. So we'll do this through the example of a predicate called max. Max has 3 arguments. The first 2 are 2 numbers, and the third is what we intend to be the maximum of those first 2 arguments. So if x is less than or equal to y, then we know that x is the maximum because it's either we know that y is the maximum because it's either greater than x or at least equal to x, in which case it doesn't matter which one it is. So if x and y are our 2 arguments and x is less than or equal to y, then y will be the maximum. What if x is not less than or equal to y? That is, this fails. Well, then we know that x is going to be the maximum, and in fact we can check to make sure that's the case, x greater than or equal to y. Now, there's a minor efficiency problem here, and that is when we get here, we know that x must be greater than y if this fails. Therefore, we could say x here and not make this check. The problem with that is that if we don't make this check, then we'll end up having poor values for x under certain circumstances. We really need to have this check in here. But the fact is that if this is true, something later fails and we try to backtrack, there's no point in doing this. So how do we get around it? Well, with the cut. And what this says is that if x is less than or equal to y, in which case we know y is going to be the max, then the cut will succeed. And what that's going to do is say, with these values of x and y, we're not going to backtrack through and try alternative versions of max. So it's never going to reach this, and we won't run into the inefficiency of trying to do this when backtracking, even when it would fail. Now, that's called a green cut. It improves efficiency. If we remove the cut, we still get valid results, and we just do a little extra work, but the meaning of the program remains unchanged. This contrasts with a red cut. Now, a red cut is needed, is a cut that's needed for correct meaning of the program. In other words, if we take out the cut, we no longer get valid results. Here's an example using max again. So here's the idea. if we have two numbers x and y, z will be the maximum if x is less than or equal to y. We'll have the cut so that if this, because, well, you can see that if x is less than or equal to y, then z should be equal to y, which is our maximum. And this cut is here so that if it's not true and we backtrack, then this one won't succeed. And in fact, if this one fails because x is greater than y, then x must be the maximum. Now, the problem with this is, of course, this is a red cut, because if I take the cut out, this is going to succeed under almost any basically under any circumstances, and we can get results that aren't valid. So green cuts improve efficiency, but they still get valid results. Red cuts needed for correct meaning of the program, and if we take out the cut, we no longer get valid results. So, a couple programming tips about the cut. First, a poor programming practice is you don't understand what's going on, and you try to fix it by just inserting cuts in there to control backtracking. Just trying out cuts to control backtracking to make up for incorrect programming is clearly a poor programming practice. What are better programming practices? Well, first, avoid using cuts in general, unless you're really clear what you're doing. Use cuts to improve efficiency and document it. And if your program does rely on a cut for behavior, in other words, you've got a red cut, document that. Let's trace the use of the max predicates we've defined and see how they work. So the first one I'm going to do, which doesn't have any cuts in it at all, I called max1. And so let's take a look and see what the maximum is of 5 and 1. And sure enough, it tells us x equals 5, and there's the only thing we have. So now let's trace this and see what happens. Max of 1, 5, x. All right. Yes. And sure enough, we get that. Now, so we get exactly the result we expected, and we get it exactly in the way we expected. Now, is max 2, which has the cut in it, going to work any differently? Let's take a look. Same exact behavior, and sure enough, we get exactly the same result. The only difference is that if something had failed later on, it wouldn't, when it backtracked, it wouldn't try to fruitlessly try the second clause for max 2 because it would fail. And now, just to show that the third version works, I'll turn trace off and let's try max 3, which is the version with the red cut. And sure enough, x equals 5. And if we look at it with the trace on, we can see it at work. So we call max 3. 1 is in fact less than 5, and therefore z gets equal to y, and we return that. And just for kicks, we'll try it with the arguments in the other order. Now it's going to fail. We try to redo it, and it succeeds immediately because if that first test failed, the other value, the x, had to be the max, and we've got it. So that's cut in a nutshell. And with that, I'll see you in class.